Hello everyone, this is Professor Iris Miano giving you your Math 50 Pre-Statistics Day 26 lecture on section 12.2, which is solving systems of linear equations using matrices. Oh, so exciting. Okay, so the first thing that we want to do is define a matrix as an array of... So an array, what is an array? It's basically a collection of numbers arranged in an orderly fashion, basically in a box. And that box is going to have rows and columns. And it's going to be a re-representation of the system of equations that it's related to. So let's take this generic system of equations that we see here. Notice the curly brace and equations 1 and 2, right? And let's rewrite it as a matrix, okay? So the way you do it is you give yourself this big bracket edge to begin with. And go ahead and start with the coefficients and constant term of equation 1. That's going to give you your values in row 1. So that'll be translated to 4 in the first position. Then give yourself some space and horizontally write the 3, which is the coefficient of the y term, and then write the 1 a little bit more space after that. Now, at this point, you can close off the matrix by putting the other bracket down, and notice that you still have some space underneath to write the coefficients and constant term of the second equation, which goes into the second row. So that'll be the coefficient of the x term is 1, the coefficient of the y term is -1. You want to make sure that there's some, signage that comes along for the ride. Oops, let me go ahead and erase that line there. And then the constant term 3 right here. So also conventionally, there's either a vertical line here or a dashed line. Now, when I was first learning this stuff in my linear algebra days, we used to put a dashed line to separate the x and the y coefficients with the constant terms. I believe later on you guys might have it in, vertical, like there's a vertical line, there's no line at all, but I generally go for the dashed line, okay? So it doesn't matter which one you add to your matrix, just so long as the numerical values are in the correct positions in the array. That's the most important thing, really. So this is still equation 1, and this is still equation 2, but they do have, I believe, somewhere in your lecture notes that were written by the department, they might be called row 1, row 2. There are other representations that are possible. Okay, and this will become, this representation might be really advantageous to us as well once we talk about row operations, or we could stick to the circled values that we did for the equation labels, with the other methods too. Just depends on what we want to do with it. So let's just go ahead and, with a couple of examples, rewrite some systems of linear equations into matrix form, and then back again with the example 2 set. So first, for part A, let's go ahead and recognize that for row 1, there is no y term here. So that's going to be represented by a 0 value in the second position of the first row. Okay, so therefore, let's just do the first row, and we'll get 3 in the x position, a 0 in the y position. Just because there's nothing there in the equation form doesn't mean you're going to leave a blank space for the array that represents the matrix. You always have to have a value there, and if there's nothing there, you're just going to put a 0 as a placeholder, okay? So that's 3, coefficient of x, 0 coefficient of y, and the constant term of 2, okay? You can close off your matrix and do a vertical dashed, solid, or no line at all to separate the x and the y terms. Let's go to equation 2's values. That'll be -5, -1, and 12 for the x and y coefficients and constant term respectively. Okay, and that's it. It's as easy as that to write the system of linear equations into matrix form. Let's do it one more time with part B. Okay, give yourself that left bracket. Start with equation 1. The coefficients are 9 and 2. The constant term is 4. That's row 1. Donezo. Okay, the coefficients and constant term for equation 2 are -3, 7, and -2. And I like to do that dashed line, so that's what I'm going to do to finish up my matrix. Cute. Okay. Now, can we start with the matrix and go back into linear systems representation? Well, sure we can. Just go ahead and let row 1 be the coefficient of the x term, the coefficient of the y term, and the constant term from left to right. And you can rewrite the top row, row 1, as 5x plus 3y equals 2. Do the same thing for row 2. -3x, 0y, so you could go ahead and just leave it blank here, equals 1. Put a little brace on the left side, and you have correctly translated the matrix into its system of equations format. Let's do that again for number 2, part B. Okay, the first row will read as 2x minus y. Remember, when the coefficient is a 1 or a -1, we don't put the 1 in front of the variable, and that's equal to -4. Okay, there's equation 1. Equation 2, there's no x term, and then there's a 7y equal to 13. Done deal. That's all there is to it. Okay, cool. Moving on. Now we need to get to know the rules associated with manipulating matrices in order to use them to solve systems of equations using matrices. So yes, it's true. In the last lecture, we went over the 3 methods for solving systems of linear equations, which included graphing, substitution, and elimination. Turns out that there's a 4th method using matrices, and that's what we're going to practice here in the next couple of examples. But first we need to get to know elementary row operations, which are basically the rules associated with playing the game of using a matrix to solve a system of equations. So the first row operation that's possible is that you can interchange rows. So here's row 1, right, is the -2, -3, 7, and row 2 is the +1, -4, +5. Turns out that you can interchange the rows and the matrix is equivalent. So that can have row 1 being 1, -4, 5, and row 2 being -2, -3, 7. So that's an example of interchanging rows, okay? Now, that's the first row operation that's possible. The second row operation that's possible is multiply or divide all entries in a row by a non-zero constant. Okay, so let's go ahead and take row 1 and divide it by, let's say, 6. Okay, so row 1 divided by 6 will yield, for this matrix, 1, 2, -3. And then, of course, row 2 is unchanged. You see that? So that yields an equivalent matrix, okay? It's totally fine for you to either multiply or divide all of the entries in a row by a non-zero constant, which is what I did here. For row 1, I divided it by 6. So is everyone okay with this notation? I hope so. Now let's go ahead and similarly, with this now modified matrix, do another one in which we multiply row 2 by, let's say, -2. So let's have -2 multiplied by row 2. And how will that change the matrix? Well, it'll still make it equivalent to even the original one, but it'll be different numbers. 1, 2, -3 will still be in the front row, or the top row, because nothing will happen there. But now let's multiply row 2 by -2, and we'll get, what, 1, 3 halves, 7 halves, or excuse me, sorry. I am multiplying by -2, not dividing. My bad. Oy. Sorry, let's start over. I am multiplying row 2 by -2. Sorry for the confusion there, folks. So if I multiply row 2 by -2, I'll have +4, +6, and -14. Sorry, does everyone see that? -2 times the entirety of row 2 will yield +4, +6, and -14. So hopefully that's clear to everybody. Sorry, I initially said the wrong thing. Okay, now, so number 3, this third row operation is definitely the most complex one. but it's the one that's necessary in order to get zeros in a certain position. And once we get into the next thing, as you can see down below this row echelon form, we're going to see why it's important for us to get zeros in certain positions in the array of the matrix that we are initially given in the process of trying to solve it. Okay, so what I'm going to do is I'm going to multiply row 1 by -2 and then add it to row 2. So here's how I can use this r sub 1, r sub 2 notation in order to illustrate that. So I'm going to take this matrix and I'm going to take -2 times r1 and add it to r2. Oops, r2 I meant. Hold on. R2. So then that will look like this. -2, 4, -6. It's going to be me taking row 1 and multiplying it by -2. And then adding it to row 2. Here's row 2 is 2, 4, -6. Okay. And that will eliminate the row or the first column value. So you'll get a 0 there, an 8, and a -12. Okay, now that becomes the new row 1, new R1. So then the matrix will then be 0, 8, -12, and we'll keep row 2 as it is, 2, 4, -6 for the time being. And then you would perform more operations. Oh, sorry, this would be the new row 2 rather. I could switch them if I wanted to. Sorry. Actually, I want that to be the new row 2. Ugh, I know that this is not making the process easier by me making errors in what I want to say. Sorry, this is going to be the new row 2. Now, why would I want it to be row 2? I'll explain in just a moment when we talk about row echelon form why I would want a 0 in this very particular position. So that'll yield 1, -2, 3, 0, 8, and -12. From there, it's just one more step in order to get this matrix in row echelon form, which I'm about to introduce. Hold on. All right, where were we? Okay, so we need to introduce row echelon form. You need to understand what that means and why we need it. Okay, so like I said before, this modified matrix is on its way to being in row echelon form. It's a matrix such that its form includes ones on the diagonal. I'll explain what I mean by that. And a 0 under each one on the diagonal. And then the rest of the values can be any real numbers, okay? So the guidelines for solving systems of matrices, systems with matrices, is to write the system in matrix form, rewrite the system so it is row echelon form. So what does row echelon form actually look like? Here's the generic version of it. You have 1, some number A, some other number B in those positions. A and B or whatever numbers, okay? So there has to be a 1 in the first column position of row 1. There has to furthermore be a 0 in the first column position of row 2, and then the next value over here in the middle has to be a 1, and then this final value in the first row can be any real number C. So A, B, and C are any real numbers. Okay, so this is what is meant by ones on the diagonal and zeros underneath the ones. Now there's only one position that's underneath the, one of the ones on the diagonal. So I'm just saying, like, in general, if you were working with a larger matrix, like a three equation, three unknown system, or 4 or 5, then you would have more zeros to think about trying to create here. So you have to use elementary row operations in order to make your given matrix take on this form right here. And that's the challenge, really. And then from there, you rewrite the system and you use back substitution to solve the system. I know. Parts 3, well, not part 3 is probably not seeming to be that challenging. Going from one form to another is actually quite easy. You just take the coefficients, or the values in your matrix, and you make them coefficients and constant terms for 2 equations. Now, using the back substitution, you might be like, oh God, that's another whole process. It's not so bad. It's what we've been doing for the substitution and elimination methods already. So we're going to just transfer that same wrap up series of steps to this process as well. The hard part really is going to be step 2, okay? That's the challenge. So we need to get to know these row operations very intimately in order to see how they will modify our given matrices to have this form right here. And I'm going to guide you, okay? Great. Let's go ahead and use matrices to solve these systems. So let's start with the number 1. And the first thing that we're going to do is make it into a matrix, right? Because at the moment it's a system of equations. Let's go ahead and transfer it into a matrix. So the matrix form of this system is going to be row 1 will be 2, -2, -10. And row 2 is going to be 1, 3, and 7. Okay, so I see row 2 in the original matrix here as a really good candidate for row 1, because look at how it has a 1 in this first position. I would really like to capitalize on that and put this row 2 in the row 1 position. Is it okay for me to switch the rows? Of course it is. That is literally the first row operation, interchanging rows. So that's what I'm going to do as my first move. I'm going to interchange the rows. So that'll give me my system looking like 1, 3, 7, 2, -2, -10. Okay. Now I need to do the linear combination of the 2 rows, basically row operation 3 that was presented, in order to create a 0 in this position. So how can I do that? Well, basically I need to use row 1, multiply all of the values of it by some very particular number, and add it to row 2 such that I create a 0 in this position. So basically I need to multiply row 1 by the opposite of this number right here in order to achieve that goal. Okay, so I'm going to take -2 times row 1 and add it to row 2. Oops, row 2, not just 2, R2. And that'll give me a new row 2. Okay, so let's have one, oh sorry, nope, I need to multiply row 1 by a -2, which will yield -2, -6, -14, and add that to row 2, which is 2, -2, -10. So add them, and this will give me my new row 2. Okay, but what will I get for my new row 2? Well, as desired, the first position value is going to be 0. I wanted those to cancel out, and I did it, so I feel good. Now, in the second column position, we'll get -8, and lastly, we'll get -28, or 24 rather, -24. Okay, so now this is my new row 2. So now my matrix has these values: 0, 3, 7, 0, -8, -24. Okay, so the last step that we need in order to get this into row echelon form is to have in the second row, I need a 1 in this first position. Okay, so here is the trick, guys. You're going to use row operation number 2 that was presented, and you're just going to take row 2, and you're going to divide it by -8. That's going to create a 1 in this position, and awesomely, but it doesn't necessarily have to happen this way, it's going to create an integer value in this position too, which is nice. So now my matrix will look like this. Row 1 is unchanged, 1, 3, 7, leave it the way it is, and then take row 2 and divide it by -8, and that will yield 0. Yes, this remains a 0, remember, because 0 divided by any number is still just a 0. -8 divided by -8 is +1. -24 divided by this -8 yields a +3. Great. Now we have it in row echelon form. The hard part is done, guys. Very exciting. I'm going to put an exclamation point there because I'm very excited about that. Now we can take this matrix and put it into equation mode. So that'll be x plus 3y equals 7 for that first equation, or for the first row rather. And then the second row will be y equals 3. You see that? 1y, or just a 1 and then the 3 there. Oh, and along the way, sometimes I drop the whole dashed line business, but like I said, it's not necessary to have it there. But anyway, this second row, when I put it back into equation form, yields y equals 3. That's half the solution set right there. So if y equals 3, take equation 1 and plug y equal to 3 into it and say x plus 3 times, not y, but 3 equals 7. So x plus 9 equals 7. That means that x has to equal -2. And there's the solution set. So that'll be -2, 3. If you want the solution to have the look of an ordered pair, here it is. Or you can, present individual solutions for x and y. And there you have it. Let's do a quick recap on this example 1. We translated the system of equations into a matrix. We interchanged the rows in order to have row 1 in this row echelon form. In order to get row 2 in row echelon form, we had to take a linear combination of rows 1 and 2. Specifically, we took -2 times row 1 and added it to row 2 to get the new row 2. Then we plugged that back, or replaced it with the old row 2 in our matrix, and then we noticed that we just needed to take row 2 and divide it by basically whatever value is in the middle position. That's kind of a borderline rule of thumb when you're at this stage of the game, and that allowed us to get our matrix completely in row echelon form. You translate it back into a system of equations and back substitute with your y value that you will get from the row echelon form of the second row of your matrix. Okay? And there you have it. Let's do this again for a different system. Let's go this example number 2. So translating this into a matrix, we will have the following. Row 1 will be 5, -3, 6. Row 2 will be -4, 5, 3. Okay, so I don't see a clear path to getting row 1 in row echelon form, because if I take row 1 or 2 and divide them by that first value, I'm going to get fractions abound. So what I might work on first is trying to get a 0 in the first position to make a new row 2 in echelon form. So I'm going to go ahead and multiply row 1 by a 4 and row 2 by a 5, and that'll make for a +20 and -20, and then those will eliminate, and then we'll see what happens from there. Okay, so let's go ahead and have our, oh, you know what? Ooh, I see actually, hold on. You know what I see? If I add these two rows together, which is a linear combination of the rows, I will get a 1 in the first position, and that'll give me a new row 1 that's in echelon form. So let's go ahead and do that actually. Take R1 plus R2. Sorry, that's supposed to be a 2. And that'll give you your new R1. So take 5, -3, and 6. -4, 5, and 3. Simply add them together, because notice that these two numbers have a sum of 1. And then -3 plus 5, that's a 2. 6 plus 3, that's a 9. So that's our new R1. So now the system reads as 1, 2, and 9, -4, 5, and 3. See what I did there? See, I didn't see that at first. I was actually going to just skip trying to get row 1 in echelon form and try and get row 2 in echelon form. But I'm glad I did this, because I think it's a lot easier now to get the row 2 in echelon form, which is going to be my next move. So I'm going to take my current R1 and I'm going to multiply it by 4 and add it to R2 to get my new R2. So let me just kind of mark this off. And so that'll give me 4, 8, and 36. That's 4 times row 1. And I'm going to add that to row 2, which is -4, 5, and 3. So that gets us eliminated as desired. I want a 0 in this first position. We will get 13 right here, which feels weird, but don't sweat it, because this last number is a 39. So that's my new R2, or row 2. So that'll give me the following matrix: 1, 2, 9, 0, 13, 39. Cool. So now simply take R2 and divide it by 13, and you will get your matrix in row echelon form. Watch this. 1, 2, 9, 0, 1, 3, because 13 divided by 13 is 1, 39 divided by 13 is 3. So here is my matrix in row echelon form. Now, translate it back into a system of equations. We will have x plus 2y equals 9. And then y equals 3 here. Okay, so y equals 3, that's half the battle. Plug this into equation 1. So that'll be x plus 2 times 3 equals 9. So that'll be x plus 6 equals 9, and that means x has to equal 3 too. So the system therefore is 3, 3. You can either represent it as an ordered pair like so, or you can individually box x equals 3, y equals 3. And that's that. Okay, let's entertain some more examples here. Make sure we really get the process down. Again, the first step is always translating your system of equations into a matrix. So that'll be -4, 2, 4 for this first row, 6, -3, -6 for the second row. This looks pretty familiar. I think I can feel what's about to happen here, but let's go through the process anyway. Let's go ahead and, as far as doing linear combinations or some such thing in order to get a 1 here, I can add them together and maybe divide by 2 later. Or I can try and get a 0 in this position. I'm going to go ahead and try that first. So let's go ahead and multiply 3 times equation 1, or row 1 rather, 3 times row 1, and add that to 2 times row 2, and then we'll at least eliminate the first column position in order to get a new row 2. So that's my game plan here. 3 times row 1, 2 times row 2, and this will give me my new row 2. So I'm skipping the process of finding a row 1 in echelon form just because it's not super easy with the rows that I've been given. Because even if I take, for instance, row 1 and divide all of the values by -4, I'll still have a fraction value in that second position. And well, if there's another way to do it that illuminates itself for me in a, later on in the process, by all means, I might want to try that. In any event, here is 3 times row 1. That'll give me -12, 6, 12. And then 2 times row 2 will be 12, -6, -12. Notice what's happening here? Not only do the first column positions eliminate, which is what I have desired, but everything else does too. So if this is my row 2, then my matrix is going to look like this. -4, 2, 4, 0, 0, 0. Whenever you have a row that's all zeros at any point in the process that you're going to be exhibiting here, that means that you have infinitely many solutions. This is akin to what happens in the other processes when you have equivalent equations in the system. Solutions. Okay, and it's because you have all zeros in a row. So when you see that, you can stop and just say, I have infinitely many solutions, and call it a day. You do not need to work any further in this matrix operation scheme, okay? Cool. Now, I believe this is the last example for us. We're going to do what we've done in all of the other examples in this section and take the system and immediately put it into a matrix. So that'll be 2, 4, and 10 for row 1, 1, 2, and 3 for row 2. Notice that row 2 is already in row echelon form for a row 1. So let's interchange the rows as our first move. Okay, now let's go ahead and take a linear combination of rows 1 and 2 in order to eliminate the first position in row 1. So I'm going to choose to take -2 times row 1 and add it to row 2, and that's going to give me my new row 2. That is supposed to say the word new, but it looks really sloppy. That's my new row 2. Okay, so that'll look like this. Oh, sorry, I meant -2, oh yeah, times my row 1, and as it's been switched in this position. I was looking at my original system at first and it got me confused. No, from this modification of the matrix, take -2 times row 1, which is -2, -4, -6, and add it to row 2, which is 2, 4, and 10. Interesting. See what's going to happen here? We're going to have the first position value eliminate and turn into 0 as desired. But notice that also the second position value also zeroes out. But what happens to the last position? If it had also zeroed out, we'd have infinitely many solutions like we did in the previous example. But that's not what happens here. What does -6 plus a +10 yield? A +4. So then the matrix becomes this: 1, 2, 3 in the first row, 0, 0, 4 in the second row. This is equivalent in the equation world as 0x plus 0y, so essentially 0 equals 4. And that is not something that we play with. We do not ever say that 0 is equal to 4 or that 0 is equal to any other number other than a 0. So this is reaching an inconsistency. This is an inconsistent system that we were working with in matrix form. And so at this point, when you have 0, 0, and then any number, C, I guess is what it was originally. Any number, C. This is an inconsistent system. which therefore has no solution. Okay, and that's that. Those are all of my matrix tricks, folks. I am happy to demonstrate more and do problems with you that you are seeing in your homework. And I can even like open up an algebra textbook that I have lying around and we can do more examples. It's really just up to you what you want to see as far as extra demonstrations are concerned if you'd like. Okay, so let me know when we see each other in class again soon. I can't wait. See you then.